Okay, so as I said before, I'm Miguel Marcelino, and I'm here to present my work on, actually our work, me and António, on a transpiler called PyJL. And our intent is actually to translate Python libraries into Julia. And actually, to give the audience a little bit of a motivation, I'm going to start by introducing the Julia programming language. And it is actually worth mentioning that Julia and Lisp have some similarities. For instance, Julia has metaprogramming, where it also represents its code as a data structure. And similar to Lisp, it also allows you to use macros. And the macros basically work with code in the format of an abstract syntax tree. And in Lisp, this would be known as an S expression. Then you also have multiple dispatch, which was another one of the main driving features of Lisp. And lastly, you also have dynamic typing in Julia. Now, actually, as a little Easter egg, I think this was demoed by Stefan Karpinski a few years ago at ALS. If you actually type the following in your terminal, this will come up. And this is called femtolisp. And it's basically a high-performance implementation of Lisp built into Julia. And you can actually see that you can actually execute normal Lisp code here. And now, our work focuses on translating Python's libraries into Julia. And well, the question that comes up is, well, why these two languages? And let's start by introducing the Python programming language. And when we actually say Python here, we actually mean CPython, because Python has many variants, like IronPython and Jython, for instance. But here we're actually working with CPython because it's the reference implementation, and it also supports Python's most recent version. So there's one advantage to Python, which is its popularity. So it currently is estimated that Python's popularity is around 28%, which is, well, 10% more than the next most used programming language, which is Java. And this also means that it influences its development. So PyPy, which is the Python package index, currently registers more than 352,000 libraries. And this includes packages and et cetera. And although Python has all these benefits, it also has some nuances. Well, the first one is that it's slow on modern hardware due to its implicit dynamism. And this brings us to, actually, we consider this the most important problem, which is called the two-language problem. So what Python users typically do is, well, they create a prototype version of their code or of their algorithm, and they write it in Python. But then when they want high performance out of it, they actually convert the kernel parts to C to obtain high performance. And this brings us perfectly into Julia. Now, Julia has a big advantage when compared to Python, which is, well, it's fast on modern hardware. And it also has another advantage, which is that it has a simple syntax. And this basically means that Julia is ideal for numerical and scientific computing. Although Julia also has its nuances, we're going to name two here. Its popularity is something to note when compared to that of Python, but here we actually also need to consider that Julia was introduced in 2009, whereas Python is now more than 30 years old. And the last thing that we want to note here is that, well, Julia currently doesn't have a lot of packages, especially when compared to Python. And actually, the importance of packages was discussed in the context of Common Lisp when developing a work called JNeil. This was a transpiler. And actually, Common Lisp did not become such a popular language, also partly due to the lack of libraries and also the difficult mechanisms used to integrate them. And Julia, on that end, has an advantage, which is that it has a good package integration mechanism. But as you can see here, it lacks some of the high-quality libraries that are found in Python. And here you can actually see that, well, Julia and Python are somewhat complementary in that sense. OK, now the question that comes up as well is, well, why are we using transpilers to do this? And here I'd actually like to present an example, which is, well, about 8 years ago, the Commonwealth Bank of Australia tried to translate its code base from COBOL to Java. And they ended up spending a lot of resources on it. So they spent around $750 million over the course of 5 years. And well, imagine doing the same thing for Python's huge library set, that is manually translating the library set from Python to some other language. You can actually already guess that this would require an enormous amount of resources. And furthermore, you'd also need to worry about translating software requirements from the code in Python to the code in, well, that other language. And clearly, an automated translation tool would benefit this process. So actually, to talk a little bit about JNeil, I introduced this a few minutes ago. And JNeil was a transpiler that translated Java source code to Common Lisp. And well, on paper, it was actually a positive thing because well, Java was and is still a very popular language. And if this was to go well, this would mean that, well, all those libraries in Java would also be available to Common Lisp, which is a benefit. And this transpiler also had another benefit, which is that it preserved the pragmatics of Common Lisp while performing the translation. And this basically means that, well, any programmer in Common Lisp could just pick up the code generated by the transpiler and just further modify it if he so chose to. But in practice, this was a little bit different. And mainly, the main problem was, well, the semantic differences between Java and Common Lisp were too big. And what was found in the translation process was that there was this impedance mismatch. So the authors actually showed a translation of Java's JOTA-time library from Java to Common Lisp. But before they could actually translate Java's JOTA-time library, they had to translate Java's standard library. And only then were they able to translate the aforementioned JOTA-time library. So it required this extra step. We're just peeling and discovering that, oh, we also need to translate this, and we also need to translate that. And this is where our solution comes in. And in our preliminary results, we actually found that translating Python to Julia can be done with less programmer intervention than what was found in JNIL. And furthermore, we can also benefit from Julia's high performance on modern hardware. And actually, PyJL, how is it built? So we actually started PyJL. We actually found an open source project called Py2Many. And PyJL is part of Py2Many. And Py2Many basically has a generic framework to translate Python into many C-like programming languages. And what PyJL does is, well, simply use that framework and implement specific, specific translation methods to translate Python to Julia. But now, for you to have a little bit of an idea how this works, we briefly present its architecture. So it naturally starts out with Python source code. This is then parsed by Python's AST module, which basically converts the source code into an AST. And this will be the format that PyJL represents its source code in intermediary transformations. And then there's the rewriters phase. And what the rewriters phase basically does is it changes the format of specific nodes in the AST so that they match that of the target language. Then we also have the core transformers phase. And this basically applies language-independent transformations. So for instance, let's imagine that you want to add scoping information to the nodes in the AST so that you can traverse it later when you're converting that AST into your target language. Then there are also the transformers phase, and this phase basically applies or adds information to the nodes in the AST. An example would be, well, imagine that you had an inference mechanism and you would want to add type information to assignments. Well, this would be the phase to do it. Then you also have the post-rewriters phase, and this phase is basically identical to the rewriters phase. It is only dependent on those previously two phases, so the core transformers and the transformers. Then you also have the configuration rewriters, and this phase is actually pretty interesting because what we found is that when you're translating Python source code into Julia, you typically have several alternatives in Julia you're translating a piece of code, and you have several alternatives to what you translate that code to. And this basically allows external files to be added with user annotations that basically change the code that is generated by the transpiler. And you'll actually see a bit of those examples throughout this presentation. Then you run the core transformers again, and this is basically to ensure that no core Py2Many functionalities were overridden by the previous phases. And then you run the transpiler phase, which actually converts semantics and syntax into Julia and actually generates the source code as a string representation. Now, let's talk a little bit about the interesting stuff now. Which is, and we'll start with dynamic behavior. And these are, now we're going to show like the things that are really important in this translation process. And we're going to start with the translation of generic operations. And for instance, imagine that you have the following code. And this is a very simple function that just returns like the first element of a container. And well, you can see that, well, you can call get first with a list. And because Python's lists are generic, you can actually mix the types of that list. And in Python, you can actually do this. You can actually call it with a string if you wanted to. Now, notice how both of these two examples, the last two examples, actually return a string. And this will actually be interesting when we actually convert this to Julia. And this is because Python actually doesn't support chars. And now, imagine we had this second function here, which is basically a generic addition function. And it just adds the elements it receives as an input. And you can actually see it. Well, you can execute this with with two integers. You can also run this with an integer and a float, where we'll just apply promotion to number 1, but that is simple. And inclusively in Python, you can do concatenation of strings using the plus operator. But now imagine that we wanted to translate this into Julia. And well, as you can actually see, well, the syntax is very similar, but what happens when you actually execute it? So the first two examples are actually fine, but when it comes to the third example, Julia actually returns a char instead of a string. And this really means that the return type of getFirst is unpredictable. And when it comes to the second example, which is actually the most interesting one, you can actually, well, the first two examples run fine as well, but when it comes to the third one, well, there's an error because you cannot concatenate strings using the plus operator in Julia. So naturally, well, for instance, in the case of the sum2 function, what we could do is, well, create a PyAdd function, which, just dynamically applies the correct operation at runtime. But this is not actually what we want, and this would not preserve the pragmatics of Julia. So naturally, we would, for instance, have a type inference mechanism, which would infer the types at transpilation time. But, well, in the case of these two functions, it's not as simple because, well, they're generic functions. And what would happen in this case, or actually what happens in this case, is that a type inference mechanism could either infer the type any, or it would perform a closed scope analysis of the types to actually try and derive the function parameters and return types. And well, to avoid generation of what previously said convoluted code, like that generating that PyAdd function, our solution currently is to just require the user to annotate function parameters and return types. And this in turn allows us to generate Julia source code where we guarantee that the behavior is also correct. Now, naturally, annotating function parameters and return types isn't enough to guarantee correctness, and this is where type inference mechanisms come into play. So we've analyzed two common type inference mechanisms for PyJL, and which are MyPy and PyType. So these are two common type inference mechanisms that you find in Python. And well, there are some differences between these two methods. Well, for instance, MyPy actually has gradual typing, and what it actually requires you to do is to annotate function arguments before it can actually infer any types, whereas PyType is, well, more of a type inference mechanism by definition, where it doesn't actually require any type annotations for you to actually infer the types. And, well, the second difference is that, well, MyPy, and we'll actually see this in the next example that we show, actually has this restriction where if you have a variable and you want to change its type, well, you can't. The first assignment will define the type of that variable, whereas with PyType, it actually allows, or it actually conforms to the legal Python usage and allows the types of the variables to change. And, well, the last thing to say is that MyPy performs intra-procedural analysis, and this basically means that it performs the analysis within the function's scopes, and that is type inference analysis. And PyType also performs inter-procedural analysis, where it goes beyond the function scopes to infer your types. But now, naturally, this is better shown with an example. So we show you this very simple function bar, where the type of z is actually path sensitive. So depending on the path you take, the variable will actually change its type. So that you can actually see here. And, well, in this case, there are two approaches that you can take. You can either take the approach of MyPy and say, okay, the variable z cannot change its type throughout program execution. Or you can say that, okay, I'm going to take the approach of PyType and actually say, okay, this is a union of type integer and string. And what we've done throughout this analysis, well, PyType actually conforms to the legal Python usage, so that's why we're currently integrating PyType over MyPy. And you can actually see here that, well, if you map this into Julia, this would be perfectly fine. It would just be generic source code. But as we're trying to generate high-performance code, as you'll see, this has a penalty. Now, this brings us perfectly into the conversion subsets. I've talked about earlier how this would, how, for instance, having such a restricted method could actually hurt the conversion subset or actually decrease it. And what happens is, well, what PyJL currently maps is, well, all of Python's data types and also the most used Python keywords. And for instance, well, let's talk first about the data types. And so you see numbers, set types, and mappings are straightforward to map to Julia. It is when you start looking at immutable sequences that there start to be some differences. So for instance, the bytes actually maps to type code units in Julia, and this basically just it's just like an immutable vector in Julia. And the byte array can be mapped to a vector of type uint8. But what is actually interesting is when we start to actually map Python's semantics into Julia. And to show you one example, we actually converted this following function, which is the Fibonacci function. I assume everyone here knows what it is. But this has one nuance, which is it uses Python's generators. And what Python's generators do is, well, underneath, they implement a finite state machine. And, well, this also implements the producer-consumer pattern. So the producer will produce a new value whenever yield is called, in this case. And whenever the consumer requests a new value, the producer will basically resume the execution state where it left off and, well, continue from there. And, well, we first started by mapping this into channels, and actually, this actually preserves the behavior of the producer-consumer pattern. But one problem is that whereas Python actually blocks before it calls the function itself or before it actually executes any instructions, well, Julia will only block at the first call to put, which is a blocking call. And this cannot be avoided even when using unbuffered channels, which have a size of 0. And, well, our solution currently is to use a package called resumable functions. And what this package does is similar to Python. It implements a finite state machine to actually convert this logic into Julia. And this preserves the behavior of Python. Now, moving on to classes, we actually present this as a separate topic to the conversion subset because we think it's a very important topic. But before we actually go into the examples, we actually need to tell you a little bit about what the differences between the OO paradigms or the object-oriented paradigms in these two languages are. And, well, let's start by telling you a little bit about what these differences are. So, for instance, Python actually uses inheritance, whereas Julia prefers composition. And also, Python actually has objects, and objects can have functions. And these functions in the context of objects are called methods. Whereas Julia, you need to define structs and functions separately. And if you actually want to define a hierarchy in Julia, whereas Python objects can extend other objects, in Julia you need to define abstract types to define that hierarchy. And then you also have single dispatch. Python only allows for single dispatch. And what happens in the case of classes, well, it dispatches on the self argument. And Julia offers multiple dispatch, which you can use functions and relate them to structs by using multiple dispatch. Now, let's go into the examples. So here we present a very simple example. So it's a class person. And the class person has an attribute called name. And it also has a getID function, which in this case, it just returns its name. And what happens if we want to map this into Julia? Well, we first need to create an abstract type to represent that type in the hierarchy. And then we can actually map the struct or the class itself with its corresponding fields using a struct. And notice that the struct extends that abstract type we've created. Now, the function getID can actually just be, well, converted into a normal function in Julia. The only thing that you need to note here is that the self argument extends abstract person instead of person because we want it to work in a hierarchy as it works with Python. Now we have this second class student, and you can actually see the hierarchy right there. So student extends from the class person, and it also defines another student number field and a different behavior for the getID function. And how you'd map this into Julia, or how the transpiler currently does it, is, well, now you create an abstract type abstract student, which extends the previously mentioned abstract person type. And what happens is now you map the fields using the mutable struct that you've seen previously. And, well, you have the getID function here. And this is basically similar to what you've seen before, but now with that new behavior. Now, the transpiler also offers a different option for you to map this into Julia, which is using a package called classes. And this package, notice how if we use this package, the syntax is actually much simpler. But now if we show you the getID method, you can actually see that the self argument, okay, I can use a pointer, actually extends from abstract person here. And this basically means that underneath, it's doing the same thing as we did before. So it's creating a hierarchy of abstract types. Now, we also want to map the student class using the same package. So here you can see the only nuance here is, well, now it defines the student number. And notice how now the other parameter, the name parameter, doesn't need to be defined because the classes package does that automatically. But notice now that it extends person. So what happens here in this case is that the class macro is internally redefining that person into abstract person to actually match the abstract hierarchy or the hierarchy of abstract types it created. And well, here the function getID is not really interesting. It maps to the same thing as you've seen before. But it still shows you that, well, it's extending from abstract student, so yeah, the abstract hierarchy is being created underneath. Oh, okay. So what if the Python user now wants other features? And for those features, we'll focus on the student class, and we'll actually just simplify it so that, just for simplicity, for our next examples. And what if, for instance, the Python user wants to define a default value for a parameter? Well, Julia structs currently don't support that, but Julia has a good functionality to actually map that into Julia. So here, for instance, we define a mutable struct now with that, that domain parameter. But now we define an extra constructor which actually holds the default value. So when we define that value in Julia, that means that that parameter now becomes optional. And what if now the user, I had some animations there. What if now the user also wants to map some logic? What if the init method also has some logic? And this is really simple to map to Julia. And well, the first part actually mapped to what you've seen before, so a mutable struct. This is what the transpiler does. But now the second part is what's really interesting. So of course you start by creating a constructor, but now you define a begin end block containing that logic now. And notice that here in the end, we also we use the new to create a new instance. So, and lastly, there's also special methods that we need to talk about. And for instance, I've named these two, but there are a lot more. What the transpiler currently does is not ideal. It just simply converts them to functions. But in the future, we would like to, for instance, convert repr, which is Python's method to actually print out a representation of this object, into a base.show in Julia, which would actually be more appropriate. Now let's go back to that previous slide we had, and you can actually see that we've handled some of the topics here. So for instance, objects that map to structs, functions, and abstract types. And we've somewhat touched on single and multiple dispatch, but what I really want to focus on here is inheritance now. And well, you can actually see that, well, Python has multiple inheritance, whereas Julia doesn't. And you can say that, okay, Julia has traits, which actually uses multiple dispatch to simulate multiple inheritance, but it's not really the same thing, because in Python you have C3 for method resolution order, and that would really not map to the same thing in Julia. And so, well, for now, we're focused on mapping single inheritance, but this will be definitely a point of future interest. Now, last thing to talk about is performance. And we've actually translated an implementation of a common benchmark, which is the n-body problem, into Julia, which has both a reference Python and a reference Julia implementation. And here, well, you can see the time of Python's reference version, which was 4.1 seconds. What is interesting, though, is the time that Julia took, which was, well, way more than what Python took, almost 3 times as much. And here, to actually discover why this was happening, because, well, we were telling you since the beginning that Julia has good performance on modern hardware. To actually discover why this happened, we took a look at the code that the transpiler generated. And here you can actually see the function that was responsible for this. And the function is called combinations, and it basically just creates combinations of objects that it receives from a list, an input list. And the code that the transpiler generated in Julia is actually pretty equivalent to the code that you see here on the left. The only problem here is this result vector, which is, well, lists in Python are generic lists, so they naturally map to a vector of type any, and this resulted in some type instability. And what this resulted underneath is, well, Julia normally optimizes vector allocations, but in this case it could not optimize them, so it just became a vector of pointers, which naturally results in much less performance. What we did in this case to actually increase performance was just to manually annotate, in this case, the result vector, which immediately gave us better performance. So in this case, we observed a 52.6 times speed up when compared to the initial result, and also it was 19.5 times faster than Python. And what this basically shows is that, well, currently the transpiler can actually translate Python source code into high-performance Julia source code with just very few changes. And, well, regarding the Julia reference implementation, well, this is still an order of magnitude faster than our implementation, but it is basically, it was a result of, it is a highly optimized version that uses Julia's performance characteristics. And, well, yeah, thank you all very much for your attention. Yeah. Please, please. For? No. This actually, when we picked up this project, it was actually not very well developed, or actually, not very. It was translating basic cases in Python, and it wasn't actually used to translate anything like large, like we want to, like libraries. So, and even basic examples in Python were failing. Like you have keywords like with in Python, which were actually not translated or wrongly translated into Julia. So no, this project actually was not used before for anything this large, at least. I think you had a question, yeah.
My question has to do with the multiple dispatch thing.
Yeah.
I didn't understand if the abstract types in Julia are like interfaces or markers. I didn't understand that.
They're similar. They're similar to interfaces. Although, for instance, you actually have Stefan Karpinski actually showed this. In Julia, for instance, you have the types. You have the simple types like integer, float, and everything. And they're actually defined as abstract types. And as you said, well, they're similar to interfaces. And the only thing is, well, they can't be extended by anything. Therefore, you have to create structs. And structs, then you can extend abstract types. So was that answered, or do you have another question?
Yes, almost, because I was thinking if you could inherit from several abstract types.
Oh, yeah, abstract types can inherit other abstract types, yeah.
And more than one?
No,
okay.
Only one. That's why it has
I don't
single
know
inheritance.
That's why I'm asking. Okay,
yeah, okay, it has single inheritance in that sense, yeah. Yeah, please.
I noticed that you worked a little bit on the matching of the semantics of the elementary types and stuff like that. I'm curious, why would you need to do that? Because what you do is you take a library in Python that has its semantics in Python, and you're going to use it in Julia, but it's not going to be used in the same way. So as long as you have partial useful semantics, that should be okay. What did I miss?
Well, it depends. It's okay as long as, for instance, you don't translate those things that you've seen from like yield. Like those need to be implemented in Julia separately.
Basic types.
Well, basic types just get converted. They can just be converted like to equivalent Julia types.
But the thing was, the type union is string or int. This is not essential for the translations.
Well, it actually depends. Yeah.
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 So say take a library in one language, move it to a different language, and all of a sudden this library becomes a little bit smaller, and a little bit different semantics. That's not a big deal because you're not going to port the code that is used in the library in most cases. You're going to port the library and have a slightly different library. That should be okay.
Well, in that sense, yes, but we really wanted to match the semantics of or actually convert this.
When you translate a library one language to another, the semantics does not have to be preserved phonetically.
Oh, in that sense, no. Okay, you're right in that sense. No, not phonetically, but it needs to be preserved in the sense that when you execute this library in Julia, it should actually output the same results.
Right.
So in that sense.
For some subset of inputs.
Yeah, exactly. For some subset. Yeah, exactly.
After
Yeah.
the next question, can you repeat the question because of the recording? He's going to ask a question, and you please.
Oh, okay. No problem.
Yeah, so for your last few slides, when you're talking about the performance characteristics, how come when you translated it from, it was just the one function collections that was causing the slowdown when you translate from Python to Julia? Yeah. But how come there was a slowdown? Because the information in you had the same exact type of information in the translated Julia program as the Python program, so I don't know, I would naively expect that Julia would be able to perform at least as well in that function, because you have a vector of generic pointers in Julia. I'm assuming, I mean, Python can't do any better than that, right?
I know,
So
I know.
how come it's worse and not the same?
Well,
We
Julia.
had the same question from online. Somebody posed the exact same question.
Oh, okay, okay. So Julia actually doesn't behave because, well, Python, first of all, you're actually talking about C in this case, so Python actually uses C. In this case, what happens is Julia can't optimize, because Julia, what it does underneath it generates LLVM code. And when you give it a generic vector, it can't optimize the code that it generates. So it's going to end up, if you actually see the differences, Julia actually allows you to see the LLVM code that was generated. And you can actually type, like, you can actually use a macro called code LLVM. And you can actually see that the LLVM code it generates. And it's highly inefficient because, well, it's not like C where you just, you write the code, you do an allocation and everything. Julia doesn't actually know what you're going to put there. So it actually has to predict all these different scenarios. So the code that it's going to compile is not going to be as efficient as Python source code. And you also have that Python is basically built for like generic operations. And you actually seen there, when we actually convert this into Julia, and we use annotations, Julia was actually able to translate or actually compile a more efficient version of that code, and that's why you get the speed up. But initially, Julia isn't as high performance in that sense if you use generic stuff. So it's just that difference between Python and Julia.
So there would be no way to make the Julia generic code do what Python is doing underneath?
It doesn't do the same thing. It doesn't do the same thing. But you can actually, Julia has one advantage, which is even if you don't give it any types, it actually performs some type inference underneath. So in that sense, you could get like largely better performance if you actually use Julia, just simply without annotations. Yeah.
Okay, that makes sense, thanks.
Shouldn't we actually repeat the last question, or?
No, because it was on. Somebody asked a question without the microphone.
Please.
Yeah, so is the idea behind this transpiler that you transpile a library once, let's say, and then further develop and improve the Julia code, or is the idea that the source of truth stays is the Python code, and so you annotate it, and when you want to, I don't know, release a new version or optimize something, you edit the Python code, and then you generate Julia again?
Actually, your question is really good in that sense, because what actually happens is, well, what if Python now releases a new version of the library? What if now there's a new version? So that's what we are working on right now, is that, well, it should be seamless for you to actually, you had code that was updated, but now Python released this new version. Oh, and it has this and these features. And that's why we had those external annotations to actually separate code from annotations. Because you don't actually want to mix code with like user annotations, because then when you go to translate that library again, those annotations will just be gone because you'll just pick up the code from Python directly. And well, in that sense, well, you can consider Python as the master version in that sense, but the idea behind this is that you can also pick up the Julia code and just start working on it. It should be seamless for you to do that, but yeah, in that sense, the Python code is the master version. Yeah. Yeah, there was one more question there.
Hello, I really enjoyed your talk. Nice talk.
Thank you.
I was wondering, how do you test your transpiler, and what's the quality of the tests?
Oh yeah, that's a really good question as well. We have like this huge testing. We have a lot of tests, and basically, we have simple unit tests, but we also test with invariants and everything. So the idea is that you have some assertion that you want to do in your Python source code. And when you convert this to Julia, those assertions should still be valid. So the code should still return the same thing, and it should have the same behavior. And that's how we're currently tested. So one of the struggles was that, well, there isn't much official testing online. If you try to find like a testing set for, in this case for translations, there isn't an official set. So we're sort of creating it right now and compiling everything we found from other transpilers as well.
Do the libraries that you translate come with tests that you can use? Or?
Yeah, that's also one of the things that we're looking at. So actually, they come with unit tests, and the idea is if you can also translate those to Julia and actually verify that the library is working. Yes, we're actually working on that now. Yeah.
Cool.
Okay. there a time?
Oh, we need to quit at 10 o'clock.
There's one question there.
Lots of interest in your question.
In the Julia ecosystem, there are also efforts underway to just flatly import Python libraries directly into Julia. How does your work compare to this? What are the pros and cons of the transpiling approach?
Are you talking about like PyCall? Okay, yeah. We actually didn't have time to test that, so we actually want to do a full comparison between what is it like to transpile Python source code into Julia, and what is the difference between using PyCall and actually just translating code to Julia. And we're currently working on that, but we're guessing that just calling Python, at least the overhead shouldn't be much different, because there was this work done a few years ago about Racket, and they found that while calling CPython they actually don't have that much overhead. The problem is, well, when it reaches Python, everything is going to be generic. So we're hoping that the source code in Julia will run much faster in that sense. And yeah, we'll have the full performance comparisons when we're actually finished. Yeah.
I have a quick question.
Yeah.
Are numerical semantics the same between Python and Julia?
Well, they're very identical.
If you do a floating point computation, you'll get exactly the same result?
Yeah, we've been testing that as well. So imaginary numbers and everything, yeah. And there's also actually, quite curiously, the transpiler currently also translates, Python has this C uint8, C uint16, and we're also translating those to Julia, because Julia has int8, int16, everything. So it actually, we found that in small and large examples, it behaves the same with the same output, even with the same rounding, Yeah.
All right, thanks everyone. Now we're going to take a break, 30 minutes. It's a little bit funny to take a break so quick, but that's how the schedule is. So we'll come back for a presentation by Sam. Did Sam show up? Good. He was lost. All right. Okay, if you want to leave anything in this room, the door will be closed.
This way?
Feel free to leave things.
Obvious.